Hey everybody, welcome to a brand new series on my channel, Topology. In this series I'm going to be going through the basics of topology at a lower level so that high schoolers can understand it. Topology is a very advanced subject and I'm learning it at the moment. I've gone through 1.5 lectures and I'll talk more about that in a second. Topology is a really advanced subject, and I'm going to try to take the material and kind of make it really easy to understand for even a high school student, So that's the goal of the series, and it really helps me learn because I learn better by teaching, and I hope it'll help you guys if you're interested in topology. And we're going to develop what topology is throughout this video series. So the lectures I've been watching and the lectures I'll be basing this series off of are by Bruno Zimmerman at ICTP, it's the institution. And yeah, I'm going to be basing what I've learned off of his lectures. So if you want to watch his lectures, feel free to do so. I'll leave a link in the description to the first video because that's what we're going to be talking about today. So yeah, let's get started. So I have my notes here, and that's what I'm going to be going off of because I want to, organize myself and make sure everything is clear and that I don't mess something up because I'm still learning this, so I don't have this memorized, and there are a lot of little definitions and axioms and theorems that you really have to know. So I'm going to be using notes. Hopefully that's okay with you. And don't think that it's like, oh, he doesn't know what he's talking about. I have done a lot of discussions with people on this subject, on these topics here, and I want to I want to make sure that you guys are confident that I know what I'm talking about, because I really in the beginning it was hard to understand, but then after these discussions I really understood what everything meant. So I'm going to translate what I've learned to you guys. Okay. So first, we need to know what a topology actually is. So we're gonna have a definition. Let me make that a little better. We're gonna define topology, right? And sorry if when I'm writing I cover the board a little bit. I sometimes tend to do that. So we're gonna define what topology is, what a topology is. So a topology, so let's say first we have a set X, okay? So it's going to be capital X, what he uses, but what I'm going to use is I'm going to use the Greek letter chi, which is, it's like a curvy X, and I'll show you what it is. But if I refer to it as X or chi or whatever, it means the same thing. I'll probably say X, but it's my chi, because my capital X looks like a lowercase x, and we're going to be dealing with lowercase x's in a bit. By the way, we're only going to cover like a portion of his lecture. It's like the first third, and I'm not going to cover everything, of course, because he has like 20 lectures. Each of them are an hour and a half, and it's just, I can't cover everything, So I'm going to cover, a few things here and there. So these videos will come out every like month and a half or 2 months or something. So yeah, so a topology, let me make that a little clearer. A topology, so this is what we're defining. So a topology on a set, and then X or chi or whatever, not a period there, is a collection. So it's a collection of subsets. Let me make that N better. Collection of subsets of X. Okay. And then there are certain requirements, and I'm going to say this is denoted, so our collection of subsets, this is denoted, he uses a written T, which looks weird. It's like this, that's like a written T. I honestly don't like it. I don't like writing it. I don't like reading it. So I'm going to use a tau. So it's kind of like this, and you can think of this as a written T. Kind of looks like a backwards J. Let me make that a little better. This is my tau, my T. Tau is often used instead of written T's if you want, or script T's. So yeah, so this is a collection of subsets of X, denoted, and I'll give you a solid meaning of what this means, such that, such that. And before I talk about these requirements, I just want you to understand what we're talking about. So we have a set X, okay? So we have our set X, right? And it's a collection of the subsets of X. So let's say we have a subset here, or a subset there, or a subset there, or a smaller one down here. So all of these subsets, so like the set of these subsets is our topology, tau, right? So that's what that means. So we have all of our subsets, and the collection of those subsets is our topology, okay? So that's what that means. Okay, so then we have specific definitions here. So the first one, so I'm going to write them up here, over here. So the first one is that the empty set, okay, so the first one is that the empty set, so actually this is part of the first one, the empty set is in our topology. So boom, boom, okay. So that's not the complete first thing. I just want to make sure you guys understand. So actually, I guess I shouldn't have, got rid of it. But yeah, so let's say we have our subsets here, kind of like 6 subsets. So we have to say that the empty set is one of the sets in our topology. Okay, that makes sense. It's just nothing. The empty set is just the set of nothing. By the way, if you don't know set theory, I would recommend looking at it for like 10 minutes, looking up some basic things like unions, intersections, stuff like that. That's really all we'll need today. Okay, so the empty set is in our topology. Also, our capital set, like the set we're talking about, X, is in our topology as well. So our entire set is also in our topology. And that makes sense because a set is a subset of itself. So I have my set here, and one of the subsets, so one of the subsets of any set is the empty set, and also itself, okay? The set of, so basically a set is a subset of itself. That's just kind of an axiom. And then plus all the other subsets inside of it. So these two are in our topology. That's pretty easy to understand. Our second requirement is that arbitrary unions of open sets are open. So arbitrary, and I'll tell you what that means. Unions of open sets are open. And by the way, whenever we're dealing with topologies, we're typically dealing with open sets. Like these are open subsets. So I can put like open here in parentheses. Okay, so what this means is, so arbitrary just means it could be infinite or not infinite. So actually let me use like a red marker to kind of annotate this. So this could be finite or infinite, right? Okay, so that's what arbitrary means. Unions, if you know set theory, you have like A union B. So if we have like a subset A and a subset B, actually let me make them two like interlocking sets, or not subsets, they're just sets. A union B is all of this, the whole thing. Okay, so arbitrary union. So this could be. So what this means is you can have a finite number of sets that you're unionizing, or you can have an infinite number. So you can have an infinite number of sets. I can just fill this board with sets and find the union of all of those sets. And then, they're all open sets. So open, it's like they're not including the boundary and stuff like that. And so this remains open, okay? So basically I'm going to talk about that here. So with our notation, let's say we have a collection of sets union capital U. So this is not the union symbol. This is just a U. So let's say we have a capital U, and then indexed with alpha. And I'll talk about that in a little bit. And this, let's say this is in our topology, okay? And then A is just an index set, so we can say it's in some set J, so we'll say this is an index set, okay? So we have, so what this means is if we have alpha and J, let's say J consists of like 10 elements, so our alpha can be any one of those 10 elements, and so then we'll have like 10 sets here. So we could have U1, U2, U3, all the way to U10, or we could, again, have an infinite number. So we could have we could just have an infinite number of U's, or sets U. So if we have sets U indexed with alpha in our topology, then, so I can say if, I should make this a capital, if, then we have that the the union, this is not the same thing as this is now a union of our sets U alpha, so the union of all of our sets is also in our topology. We have to make it clear that alpha is still in our set J, okay? So, this is a lot to take in, but basically what we're saying is that the union of all, so if the union of our sets is in our topology, so let's say these are each of, like this is U1, U2, U3, I can actually label these U1, U2, U3, U4, U5, and U6, okay? If each of these are members of our topology, then the union of all of these is also in our topology, and that makes sense. That makes sense when looking at this here. You know, if I take the union of all of these, and maybe there are a bunch more, this is still going to be in our topology. So that's really good. And note how we're talking about, we're not saying they're subsets of the topology, they're elements of the topology. And we'll talk about the distinction between that, I think, in the next episode or something. But yeah. And so then the third, I guess I kind of went weird here. The third one is, that finite intersections, so finite intersections of open sets are open. I'll just continue it here. Open sets are open. If they're open, they're in our topology. So that's kind of what that means. Okay, so finite intersections of open sets are open. So here, remember, we could say arbitrary. It's finite or infinite. Here it has to be finite. And so there's a kind of specific reason to that, and he does go through it briefly in the lecture, so I'll let you watch that if you want. Okay, so finite intersections of open sets are open. I think I made this very slanted. Let me just rewrite that. Okay, so I hope you can see this. Finite intersections of open sets are open. Okay, so basically we can write this with some more notation here. So intersections would be something like, let me stay consistent here. So finite is, of course, just a finite amount, not infinite, so this would be A intersection with B, right? By the way, when we're writing stuff with this notation, this, you know, we could have if we put the U in the front, like the union symbol in the front of our sets, that's just, you know, if we're doing like a larger amount of sets, stuff like that, because this is just for two sets, you know, we're taking a union of two sets. You could do A, U, B, U, 3, I'm sorry, A, U, B, U, C, you know, you could do it like that, but if you have like a bunch of sets, you can just do it shorthand like this. Okay, so he kind of does it this way. I want to stay consistent with the way he did it here. So if we have, actually this is kind of the same thing. So yeah, so I'm going to index this with beta, just I don't want to confuse it. So if we have our union, or I'm sorry, our sets U beta in our topology, and beta is in our set, I don't know, I'll just say capital K, make this beta a little better. Okay. And also we need the restriction that K, our set K, has finite cardinality. I'll just say K is finite, or has finite elements. Yeah, K has finite number of elements. So we can't have like an infinite number of elements, because then that wouldn't work for this. So if our set's U and beta, U sub beta, index, this is our index set, K is our index set. If these are in our topology, then, the same thing is true. So then we can say that the intersection, let me make that more clear. I'm sorry, I keep having to erase stuff like that. The intersection of our sets U sub, I said beta, U sub beta, this is still in our topology. And we also note that beta is in K. Okay, when I'm writing down here, it's a little more difficult. So beta is in K, right? Okay, so that's basically our third condition, and these are our three conditions. We have, let me just make it easy to see. So we have our first, our second, and our third conditions. So if these three conditions are met, then our collection T or tau, that is then considered a topology. And that's it. So that we went through a lot today. The definition of topology. I hope I made this easy to follow. Of course, if you have any questions, leave them in the comments below. And if you just want to learn more about this and see another perspective on this, definitely check out Bruno Zimmermann's lectures, okay? That's what I'm basing this off of. I'm not like copying any of his stuff. I'm just basing it off of his work here. Okay, so again, check out his lecture series if you're interested. Ask me questions in the comments. I'm not an expert, but I will definitely try to help you if I can. Thank you so much for watching, and I will see you in the next episode, which will come out in a while, but still, I'll see you then. Bye, guys.